Hi everyone, so today we're going to be looking at some tree diagram questions that will help us solve some probability questions here. So if we look at the first question, we've got Tina. She has two bags of counters, bag A and bag B. Now there are 5 red counters in bag, there are 5 red counters and 3 blue counters in bag A. And there are 4 red counters and 5 blue counters in bag B. Now what we have to find is we have to find that she takes a random account from each bag. So first she takes a counter from bag A, and then she takes a counter from bag B. And from that information, we now have to first create a probability tree diagram. And then using that tree diagram, we have to find the probability that Tina takes 2 blue counters. So first of all, what makes this a tree diagram sort of question? The one thing you need to understand mainly is that we use tree diagrams when we have a multi-event sort of situation. So when someone's performing 2 different tasks or 3 different tasks or more than one task, we use probability trees to show each of those events. So we can see over here, Tina's going to be doing 2 things, right? She first takes a counter from bag A, and then she takes a counter from bag B. So in these sorts of situations is where we use a probability tree diagram. If we look at the answer for this example, for this question, again, I've just got the main information here. So we've got 5 red counters and 3 blue counters in bag A. So we've got a total of 8 counters in bag A. And then we've got 4 red counters and 5 blue counters in bag B. So first, to draw the probability tree diagram, we start off with bag A, as you can see over here. And then what we do is we draw up the two different outcomes that she can get. She can either get red counters, or she can get blue counters. What's the probability of getting a red counter? It's 5, because there's 5 red counters out of a total of 8 total counters in the bag, and then it's 3 out of 8 for getting a blue counter. Okay, and then that's bag A done. Then she next gets a counter from bag B. Now in bag B, there are 4 red counters and 5 blue counters. So there's a total of 9 counters here. Right, there's a total of 9 counters in bag B. So the probability of getting a red is 4 out of 9, and the probability of getting the blue is 5 out of 9. And that probability stays the same, regardless of whether she draws a red counter or a blue counter from the first bag. And then the reason for that is because they're different bags. So the number of counters doesn't change, right? If she was getting 2 times from the same bag, say she got a red counter already, there wouldn't be 5 left. Now there would be 4 left. So the probability here would be 4 out of 7, because there's 7 total counters left and 4 of them are red. We're not doing that though, since we're dealing with 2 different bags, so it makes it a little bit easier in our case, and that's what our probability tree diagram would look like. Now to answer the second part of this question, we have to work out the probability that Tina takes 2 blue counters. So what that means is that we want a blue counter from bag A, and then we want a blue counter from bag B. Okay, what's the probability of getting a blue counter from bag A? It's 3 over 8. And what's the probability of getting a blue counter from bag B? It's 5 over 9. So the probability of getting both of them blue is we would multiply them together, which would give us the simplified fraction 5 over 24. And that's a probability that Tina gets 2 blue counters. Right, looking at the next question now, we've got Bradley, and he gets the bus on Saturday and Sunday. The probability that Bradley's bus will be late on any day is 0.2. Now from this information, we have to first create a probability tree diagram again, and then we have to work out the probability that Bradley's bus is late on at least one of these dates. So again, how do we do that? First, we need to determine what our outcomes are, right? So again, we've got 2 events. The 2 events are him catching the bus on Saturday and then on Sunday. And then, so yeah, he's catching a bus on Saturday and Sunday. And the 2 possible events that can happen is that his bus is either late, or it's on time, or it's not late, right? Now we know the probability that Bradley's bus will be late is 0.2, right? And that means that the probability that the bus will not be late is going to be 0.8. And that stays the same on any given day. So that's the same probability for both Saturday and Sunday, right? So that's our tree diagram there. Now, the second part of the question asks us to figure out the probability that Bradley's bus is late on at least one of these days, right? So the easy way to do this is, what this means is that if Bradley's bus is late, we need to find the probability that Bradley's bus is late on at least one of these days. So that means that the bus can either be late on Saturday, it can either be late on Sunday, or it can be late on both Saturday and Sunday. Okay? So the only thing it can't be is that it can't be on time on Saturday and Sunday, right? So that's what we're going to, that information is what we're going to use. As you can see here, the probability of him being late at least one day, or the bus being late at least one day, is equal to 1 minus the probability of the bus being late on none of the days. So which we can get from these two numbers here. So the probability of the bus not being late on Saturday is 0.8, and the probability of the bus not being late on Sunday is also 0.8. So if we do 1 minus that, we'll get this as our answer. And that represents the probability that he's going to be late on at least one of the days. So this is an easier way to do it, rather than, you know, figuring out all the other possibilities. Like you could do late times late times not late, and not late times late. You know, adding all of those up, you'll still get the same answer. This is just an easier way and a quicker way to do it in probability. Now the last question here is with Lola here, who plays a game where she can win, draw, or lose. That's a bit important, and we're going to come back to that in just a moment. So the probability that Lola wins any game is 0.6. The probability that she draws any game is 0.1. And again, it's a multi-event situation because we're given the fact that Lola plays 2 games. So immediately we know that we need to use tree diagram because it's a multi-event situation. And here we need to work out the probability that Lola wins exactly 1 game. Now the reason why I said that that this part is important here is because in all the other examples so far, we've had 2 events, right? In the first example, we had the event that Tina picks either a red counter or a blue counter. And in the second question, the only possible events were that the bus was either late or it was not late. Here though, we have 3 possible events. She can either win, she can draw, or she can lose. So that's just something a bit extra that we need to take into consideration. So if we look at the solution for this question here, we can see we're first drawn up the tree diagram again. So let's have a look. So then we're set up our 2 events as game 1 and game 2, and we're set up our 3 events. She can win, draw, or she can lose, right? The probability that she wins is 0.6 as we're given here. The probability that she draws is 0.1 as we're given here, and that therefore the probability that she will lose is going to be 0.3. Now, we need to work out the probability that Lola wins exactly 1 game, right? So there's a few different ways that this can happen, right? She can either win the first game and draw the second game. She can win the first game and lose the second game. She can draw the first game and win the second game, or she can lose the first game and win the second game, right? So that's all the probabilities that we have here. So she can win and then draw, that's 0.6 times 0.1. She can win and then she can lose, that's 0.6 times 0.3. She can draw and then she can win, that's 0.1 times 0.6. And then she can lose and then she can win, that's 0.3 times 0.6. Adding all those up, we get our final probability as 0.48. So a bit more work required in that one. But yeah, these are how we solve these sort of tree diagram questions. Drawing up the tree diagram is usually the hardest part. Once you've got that information down, solving the actual question, it's pretty straightforward.